Okay, so we are continuing our journey to answer the question derivative, what is it good for? And this is the beginning of section 4.2, it's day 1. So the essential question is, how can the mean value theorem be applied to different functions? So this essential question is kind of really specific. And there's more in the section than just this, but this is kind of the meat and potatoes of section 4.2. So we know that in algebra the word mean means average, and you know, the word mean in other areas like in English class or something is totally different. But in math, it means average. And so if we go back to the beginning of the year in Unit 2, we know that if we are talking about an average rate, which derivative is a rate, then we are talking about our algebra slope. So if we look at this expression down here, you can see on the right-hand side is the expression for the algebra slope. So Theorem 3 says, for the mean value theorem for derivatives, says if y, which equals f of x, so if we have a function and it's continuous at every point in some closed interval, and we can differentiate it, so no cusps and corners on the inside, so no cusps and corners on the inside, then at least one point, we can find a point C where we can find an algebra slope between the endpoints, right? These are the endpoints A and B. We can find the algebra slope, and that's equal to the slope of the curve, the derivative of the curve. So if, for instance, if we look at this trinomial, this third degree function here, and we pick just a random point A and a random point B, and we connect those 2 points, we can find our algebra slope. We can do a rise over run. And so somewhere in between A and B, so now I'm looking at this part of the statement, at a point in the interior, somewhere on the inside between A and B, there's going to be this point C, where when we draw a tangent line, that tangent line is going to be parallel to this algebra slope. So if you can kind of picture this line scooching upward, it's going to be tangent to the curve at about this location C. So that's got to happen at least once. That's a guarantee as long as the function is continuous and differentiable. In other words, continuous, in other words, we can't lift our pencil. Differentiable, in other words, no cusps and corners on the interior. This is going to happen at least once. It's a guarantee. So for instance, if I were to extend this line all the way across here and maybe pick point B to be way out here on the right where my pointer is, this would happen twice. It would happen once up here and once down here. So it's got to happen at least once. That's a promise. And out of this theorem comes this little caveat over here on the left, and it's called Rolle's theorem. Rolle is a mathematician back in the day. And Rolle basically just said this about the mean value theorem. Rolle said, hey, let's take 2 points, A and B, but let's take the 2 points in such a specific location such that when I draw the line between them, I get this horizontal line. And we know that horizontal lines have 0 slope. Because this function is continuous and differentiable at every point between A and B, we've got to be able to find another location that has 0 slope in between. And we know that locations of 0 slope are those mins and maxes, or hills and valleys. So Rolle's theorem is a way to find those hills and valleys using the mean value theorem. So we've got that point C, and now Rolle's theorem, like I said, it's a special situation, so it's a special caveat that locates in this case, our hill. And so just to put this in everyday terms, kind of a working definition, we see this, we know that's the derivative expression. So the derivative equals, that's that math symbol, algebra slope. So there's our kind of our working definition, and in this working definition, is where our strategy lies. We're going to take the derivative and set it equal to the algebra slope to find these locations C. So let's try this. We have this function. It's x, f of x equals x to the 2/3 power. So a 2/3 power is a squared followed by a cubed root. And so we're going to have a cusp at 0. And if you notice, first of all, it says show that this function satisfies the mean value theorem on the given interval 0 to 1. And so let's take a look at this interval from 0 to 1. It's this region right here on the graph. So we start at 0, we end at 1. And if we notice that although we have a cusp here at the end point, we do not have a cusp on the interior. So we're okay to use the mean value theorem here. We just can't have any cusps on the interior. So let's go after our algebra slope here. So our algebra slope is finding the slope of that line between 0 and 1. So we need the function value at 1 minus the function value at 0 over 1 minus 0. So the function value at 1 is 1. You can read that right off the graph, or you can plug 1 into the function. 1 to the 2/3 power is 1. 0 to the 2/3 power is 0. So this slope is 1. And we can see that on the graph, right? If we look at this red line on the graph, it goes up 1 and right 1. So our rise over run is 1 over 1. So we're going to set that equal to our derivative. So taking a look at this function here, we have to differentiate this function. So it's a continuous function. It's differentiable everywhere. So let's go ahead and take the derivative here. We'll bring down the 2/3. And so we got 2/3 x to the minus 1/3. So that is 1 smaller than this power. And we need to set that equal to 1. So I'm rearranging this. It's 2 over 3 times a cubed root of x. And that equals 1. And now I'm going to solve this expression for the value x. And that's going to become my c. So in order to solve that, I can say this 1 is really 1 over 1. And then I can cross multiply. 2 times 1 is 2. 1 times this is this. And then I'm going to divide by 3. And then I'm going to cube both sides. And so then the right-hand side is just x, and the left-hand side is 2 cubed, which is 8, over 3 cubed, which is 27. So at 8/27, which is about right here, at 8/27, I have this value. This is my c, my 8/27, and it's at this location where if I draw my tangent line, it has also a slope of 1, the same as the secant line. So, so this is my value c. So the tangent line through point 827, 49, that's just the y value, is parallel to the secant line between 0, 0, and 1, 1. So if we would change the domain, like pick 2 different x values where the mean value theorem or Rolle's theorem cannot be applied, we would pick like a domain from -1 to 1. If we picked that domain, then we would have the cusp on the interior, and we would not be able to use the mean value theorem at all. Likewise, if we would pick the domain -1 to 2, again, the cusp is still on the interior, so we would not be able to use the mean value theorem. Here's another example, -2 to 1. Again, we cannot use the mean value theorem because the cusp is located on the interior. Same with -2 to 2. And we could keep giving examples. We could give examples like -3/2 to 3/2 or something like that. So, but because of our original problem with the cusp being at the endpoint, we're okay to use the mean value theorem for that. So any domain that includes this x equals 0 point where the cusp is on the interior would not be able to use the mean value theorem. And that's because we don't have we are not differentiable at 0. It's a cusp there. And if you look back at that definition of the mean value theorem, we have to be differentiable on the interior. Okay, so we're going to switch gears here a little bit. And the mean value theorem is what it is. It helps us find locations for tangent lines. It also helps us find mins and maxes if we want to apply Rolle's theorem. But we're going to switch gears a little bit and talk about increasing and decreasing functions again. And we've been talking about when functions increase and when functions decrease a lot. And so now we're going to kind of get to the meaty stuff of what that means. So if we look at this function here, it's a third-degree polynomial. And increasing means it's trending upward. So if we notice it's trending upward here where this blue arrow is, and it's also trending upward here, starting at this min and going up to that location. So we know that the function is increasing in those two domains. If you also notice, though, if we look at the derivative values in those two regions, the derivative is positive. So a function is increasing over an interval if the derivative is always positive. So that's kind of what we're getting out of it, is increasing functions have positive derivatives. And likewise, the decreasing portion, so if we look at this, where this red arrow is, this is where the function is trending downward. So this is where the function is decreasing. And that decreasing domain, notice the derivative is negative there. So a function is decreasing or trending downward in those intervals where the derivative is negative. So the nice thing is we don't really need a picture of the function itself. We just need to know whether the derivative is positive or negative to see if the function is increasing or decreasing. So, so we call this the first derivative test. And basically the first derivative test is saying if the derivative is positive, then the function is increasing. And if the derivative is negative, then the function is decreasing. So that's kind of what it's saying. In other words, it's saying I don't have to use function values anymore, which is what we were looking at before. So this top box was how we were kind of looking at it before, where you were using function values. Now we can say, all I have to do is look at the derivatives. I don't need the function values at all. So that's kind of the first derivative test. So it's just looking at increasing and decreasing functions a bit different. And so it's sometimes we call it the F-prime test. So our strategy then for increasing and decreasing, we're going to stick with steps 1 through 5 for finding extreme values. That we did an anchor chart with that, and it should be up on the board. And we're going to add a step 6 here, which is going to be the first derivative test. And so we're going to do that first derivative test and look at those derivative values. And then 7 is really, actually 7 is tied up in steps 1 through 5. If we're going to sketch the function, we'll grab some function values. So let's try this with this function here, x cubed minus 3x. So and the question is where is this function increasing and where is it decreasing? So another way we can ask that question is where is the derivative positive and where is the derivative negative? So the first thing we need to do is find the derivative. So what strategy we can use? We can use our 5-step method. And so let's find that our hills and valleys. That's where our derivative is equal to 0. So the derivative of x cubed minus 3x is going to be 3x squared minus 3. And we're going to set that equal to 0. And then we're going to solve that. So we can factor out a 3, or divide out a 3, and then we can either factor this or move the 1 to the other side. I think I decided to factor here. And so we know that x equals minus 1 is a location where it could be a hill or valley, and also x equals positive 1 is a location that could be a hill or a valley. So it's where the derivative is equal to 0. So so if we look then, and we can just kind of cover ourselves here, cusps and corners. Here's our derivative. In order for there to be a cusp or a corner, we need a fraction with x in the denominator, and there's no fraction here, so we know that we have no undefined derivatives, and so since the derivative is not a fraction, we have no cusps and corners. If you wanted to skip 2 altogether because you knew that even before I said anything, that would be fine also. So let's start to kind of put this together. So like I said a screen or two ago, we have a 0 derivative at -1 and a 0 derivative at +1. So I put those on the derivative number line. And we're going to grab the function values at those critical points. So we're just going to do that step 3 real quick. Find the y values for the hills and valleys. And so when we plug -1, now we're finding function values. So we're going up here to this original function. Plugging in -1 here gives me -1. Plugging in -1 here gives me +3. So -1 plus 3 is 2. And then when I plug in 1 into my function, so I know I have a function value of 2, so I go ahead and put a point at 2. When I plug in 1, I have 1 cubed, which is 1, minus 3 times 1, which is -3, so that's -2. So I know I have a function value of -2 here. So just by inspection, you can see that this is a hill and that's a valley. And so what we're going to do now is we're going to focus on this derivative number line so that we can kind of fill in the gaps here between these points. We don't have any endpoints, so that doesn't even factor in. So notice I'm up to step 6 here. Step 5 is making this number line, but if you make the number line as you go along, then step 5 you never end up having to do anything. So step 6 says find the derivative values between the critical points. So in other words, here's a critical point and here's a critical point. So I need a derivative value here, and I also need to have one here and here. So in order to find derivative values, I have to pick a point to plug into the derivative expression. So I'm going to pick -2. So I'm going to find the value of the derivative right here, the value of the slope of the curve. So when I put -2 in here, I get 4 times 3, which is 12, minus 3 is 9. Now, I mean, it's nice to know that the derivative is 9, but we never really graph that value. What I really care about is that the value is a positive value. Because if the derivative is positive here, then it's positive everywhere on this side of the critical point. There's nothing out here that would make the graph bend. So we know that the derivative has all positive values in this region, which means we have an increasing function. So that means that in this region, we have something that looks like this, a function that's increasing up to this max. And then I'm going to check this region now. So I'm going to pick x equals 0 to plug into my derivative function. So when I plug in 0, I get -3. Again, it's nice to know that the derivative is -3, but really the only thing I really care about is that the derivative is negative. So I'm going to put, since the derivative is negative at 0, the derivative is negative everywhere between these critical points, because again, there's nothing here in this domain to cause the function to bend and to change direction. So the derivative values are all negative across this domain, which means I must have a decreasing function from this point all the way to that point. So it must look like that. And then I'm going to try a point out here. So I'm going to try 2. And plugging 2 into the derivative expression is going to give us a value of 9 again. And again, it's not so important that it's 9, but what is important is that it's positive. And so I know that since it's a positive derivative at 2, it's a positive derivative everywhere on this side of the critical point. And so we know we have an increasing function in this region. And so that function just continues to increase. So our function then must look like this. So we have an increasing function. And this increasing function, the function is increasing here and here. So we can list those as domains like this. Oh, that's a typo. That should say negative infinity. Should be a negative sign right there. Negative infinity to -1. And again, starting at 1 and going to positive infinity. And then a decreasing function is in this region, this domain, from -1 to 1. So again, these are domain. These are listed domains. And again, this should be a negative infinity right here. That's a typo on my part. Okay, so we're kind of switching gears once again. So now we're switching gears. So we've talked about 2 major things in this in this section 4.2 so far, mean value theorem and the first derivative test. And now we're talking about a third very distinctive thing. 4.2 is kind of a hodgepodge that way. So now we're going to kind of talk about how I can find a function when I know its derivative. So for instance, what if you know that the derivative is equal to 0? Then what could the function be? And so we know that if we get a derivative of 0, we must have had a function that was a constant value. So in other words, like f of x equals 2. That has a derivative or a slope of 0. So that could be a possible function, but it's not the only one, because we could also, like, say g of x equals -3. You know, that also has 0 slope, so it could be this function as well. Or we could say h of x equals pi. You know, that's a possibility too, because that also has 0 slope. So we have these possibilities. We don't quite really know what the function is. But if you notice, all of the functions that it could be are kind of in the same family. They're in the family of horizontal lines. So, and we know this because their slopes are all 0. So, so, while we can't nail down the function specifically with just this information, the value of the derivative, we can say that it definitely falls into this family of functions. So what we can say then is that so if we take a look at, let's say, this function, okay, and we'll get back to what the step at the top of the screen means in just a second. Let's try to figure out what function this is. And so again, we have to figure out, well, if this is the derivative, what did I start with that when I differentiate it gives me 3x squared? So if you think about it, x cubed, when you differentiate it, 3 comes down, and this power changes to 2. So this first term must be x cubed. And the second term, what did I start with to get the derivative of 6x? Well, I know I had to start with a power of 2. And then because when I differentiate it, it'll give me just an x, a power of 1 in other words. And that 2 is going to come down in front, so I must have had a 3 there to begin with, so that when I differentiate 3x squared, I end up with 6x. So this is a possibility of what we started with, the function we started with. And so x cubed minus 3x, it's graphed right here in blue. And so that's a possibility, because when I differentiate this, I definitely get this. But is it the only possibility? So my question is, well, couldn't I have said it was this? Because if you look at this function and differentiate it, you also get this. Because you also get 3x squared minus 6x. So the fact that I have a plus 1 at the end, it changes the function, but it doesn't change the values of the derivatives. So if you look at the blue graph and the red graph, we can see that the slopes are the same everywhere on those graphs. It's just that the red graph is shifted up once. It's got an offset. So we could also say it's this graph. Now we could shift it up 3 to be that yellow graph. So, so this constant off the end here is something that's going to offset the graph, but it's not going to factor into the derivative. So what we say is that functions with the same derivative differ by a constant. So in other words, if we look at these 3 functions here, f and g and h, they're all different. And their difference is this constant right here. Because once we differentiate this, these constants go away. So, so that means that in general, what we say is that this function is x cubed minus 3x squared plus c, some generic constant that's going to give us some offset here. And the value c is just going to, it's going to be something we have to find eventually. So let's try this here. Let's find a function whose derivative is sine x. Okay, so so you got to think then. Okay, I've got some function, and when I take the derivative of this function, I get sine x. So trial and error. Well, let's start differentiating cosine x. Well, the derivative of cosine x is minus sine x. That's close, but it's not positive sine x. So let's just tweak this a little bit. Let's take the derivative of minus cosine, which is going to be minus a negative sign or a positive sign. So this is it. So the function must be minus cosine. So, but the thing is, we don't know if it's minus cosine plus or minus some number. So what we say then is it's minus cosine plus c. In other words, we acknowledge we could have some number out here. And when it's differentiated, it would just go away. So we have more information, though, than what I've given in the past. So in other words, we've got this derivative, it's sine x, and this is the new information. It passes through the point 0, 2. So what that means is that when x is equal to 0, y is equal to 2. So I can put that into the expression. When x is equal to 0, y is equal to 2, and I can find that value c. So we know that the cosine of 0 is 1. So this whole term becomes negative 1. So we have that 2 equals negative 1 plus c, so c must equal 3. So this function must really be minus cosine x plus 3. So if you notice, we had to have this initial coordinate 0, 2 in order to find that value c. So when I graph then this cosine, I can see that at x equals 0, this value is negative 1, and so we end up with a graph with a value at 2 when x is equal to 0, and we know that we have a minus cosine graph, which means that it starts low and goes up high. So at this point, you can start to look at your 4-2 mean value theorem day 1 homework.